Okay, let's talk about the first isomorphism theorem for rings. Follows exactly like the one for groups, but this is such a fundamental thing, I think it doesn't harm repeating it. You can consider it as a revision of the previous one. And it would follow from this master theorem that we did, so I have quoted it here. I'll remind you what the setup was of this theorem. So you're given three rings, A, B, and C, two ring homomorphisms, a ring homomorphism F from A to B and a ring homomorphism G from A to C, and you want to ask when can I find a ring homomorphism from B to C such that F, applying F and then applying this dotted homomorphism amounts to applying G. And the answer is that if F is onto, which we denote like this, and if the kernel of F is in the kernel of G, that's this key condition here, then there does exist such a homomorphism. And in fact, it's a unique one. There exists a huge, and one puts exclamation mark to say that it's a unique one, such that this diagram commutes, as we say, meaning applying F and then applying H amounts to applying G. Okay. This is the content of part A of 2 of this theorem. I erased part 1 because we don't need it. And then part D says that if G is also onto and if the kernels are actually equal, then H is actually an isomorphism. All right, so now here's the first isomorphism theorem. For rings, so it's literally the same statement as you had for groups, except you want to change the word group homomorphism by ring homomorphism, and the word the kernels are now ideals rather than normal subgroups. Let psi from R to S be a ring homomorphism, and let I be the kernel, and let phi from R to R mod I be the natural quotient homomorphism, so this is the map that takes an element R to the coset of R. This is a onto ring homomorphism whose kernel is just I. Okay, we talked about this when we constructed this quotient R mod I last time as a ring. Okay. Let's read this again. So psi is a ring homomorphism from R to S whose kernel is I. Once you give me this I, which is a two-sided ideal in R, I can construct the natural quotient homomorphism phi from R to R mod I, taking an element to its coset. The statement is that then there exists a unique isomorphism eta from R mod I to the image of psi, such that psi is eta circle phi. Alright, so let me draw the diagram, and that would say a lot more. Okay. Proof. First of all, note that this I, which is a kernel of a homomorphism, so it's an ideal in R. This means two-sided ideal. Okay. So what's given? What is given is that you have this R to S homomorphism called psi. This one is not onto, but if I restrict it to its image, which is really a subring of S. Now this one is onto. Okay. You're also given a homomorphism from R to, you're not given, but you can construct this natural homomorphism from R to R mod I called phi. Yes. And the kernel of psi is I. That's the definition of I. But the kernel of the quotient map phi is also I. And this quotient map is also onto. So we are exactly in the setup of this theorem here on the left hand side. And what does it give us? It gives us that there exists so by 2a of the theorem there exists a unique ring homomorphism. H from R mod I to psi of R. Oh, we just choose to call it eta in the theorem, so we'll call it eta. Such that going down right, meaning applying phi, and then applying upright, same as applying psi. And note, the kernels are actually equal, and both these maps, phi and psi, are onto. So our G, which is psi in this case, is also onto. So part D of the theorem actually applies. So I could say by part D, this is isomorphism. Maybe I should also note psi is onto and the kernels are equal. So by part D we have this isomorphism. What does this mean? That means in particular, so that proves the theorem. So in particular, if psi from R to S is a surjective ring homomorphism, so the image is really all of S, then what this is telling you is that R mod the kernel is in particular isomorphic to the image. Okay? But it's actually telling you what this isomorphism is. R, this psi induces an isomorphism. That's what it's telling you. Yeah. So this takes a coset A plus I to wherever psi would have taken A, where I is the kernel. And it's inbuilt into this that this is well defined.